So now we will comes to characteristic root theorem. So definition is given that if T belongs to AB, then lambda belongs to F is called characteristic root or eigenvalue of T if lambda minus T is singular. So theorem 1, let lambda belongs to F is characteristic root of T belongs to AB, then lambda minus T is singular. Then there exists a V not equals to 0 in V such that V of lambda minus T equals to 0, V lambda equals to Vt, that is Vt equals to V lambda. Conversely, let Vt equals to V lambda for some V not equals to 0 in V, then Vt minus V lambda equals to 0. V अगर कॉमन जाएगा तो T minus lambda equals to 0, then lambda minus T equals to 0, which implies lambda minus T is singular. So lambda is a characteristic root of T. Similarly, comes to next lemma. If lambda belongs to F is a characteristic root of T belongs to AB, then for any polynomial Qx belongs to Fx, Q of lambda is a characteristic root of Qt. So in proof, let lambda belongs to F is a characteristic root of T belongs to AB, then lambda minus T is singular. By theorem, there exists a small v in V such that V of lambda minus T equals to 0, that is Vt equals to V lambda, then Vtt equals to V lambda T, lambda Vt square equals to lambda square V. Similarly, Vt to the power m equals to lambda to the power mv for all positive integers m. If Qx equals to alpha 0, alpha 1 x1 plus dot dot alpha m xm, then Qt equals to xk plus में t, then V of Qt equals to V of whole this polynomial term, then V अगर अंदर चलाएगा तो alpha 0 V plus alpha 1 V t1, alpha 2 V t2 plus dot dot alpha m V tm, then alpha 0 V plus alpha 1 V t1 equals to lambda 1 V plus alpha 2 lambda square V plus dot dot alpha m lambda m V, then alpha 0 plus alpha 1 V1 plus alpha 2 lambda square plus dot dot alpha m lambda m. Then this is your V of Qt minus Q of lambda t equals to 0 because this is your Q of lambda. So Q of lambda is a characteristic root of Q of t. So if lambda, in next theorem, if lambda belongs to F as a characteristic root of T belongs to AB, then lambda is a minimal polynomial of T. In particular, T has only finite number of characteristic root in F. So let lambda belongs to F is a characteristic root of T belongs to AB, and Px be the minimal polynomial for T, then Pt equals to 0, then V of Pt equals to V of P lambda, then V of P lambda equals to 0, and P lambda equals to 0, then lambda equals to root of the minimal polynomial for T. So let dimension of V equals to n, then degree of Px less than equals to n square. So Px has at most n square roots, which implies there can be only be finite number of characteristic roots of T in F. So if T comma S belongs to AB and AB is regular, then T and Ts inverse have the same minimal polynomial. So proof, as S is regular, S inverse exists, so ST S inverse का square equals to ST square S inverse. Similarly, ST S inverse of I equals to STI S inverse. Let Qx belongs to Fx and Qx equals to alpha 0 plus dot dot alpha k x to the power k. Then Q of ST S inverse equals to this. If Qx is a minimal polynomial for T, then Q of T equals to 0, then Q of ST S inverse equals to 0, which implies Qx is a minimal polynomial for ST S inverse. Then theorem, if lambda 1, lambda 2 up to lambda k in F are distinct characteristic root of T belongs to AB, and if V1, V2 up to Vk are characteristic root vectors of T belongs to lambda 1, lambda 2 up to lambda k respectively, then V1, V2, Vk are linearly dependent over F. In proof में given है, let k greater than 1 assume the contrary, Suppose V1, V2, Vk are linearly dependent over F, then there exists alpha 1, alpha 2, alpha k belongs to F, not all zeros, such that this is a linear combination. There may be many such relations such that V1 beta 1 plus V2 beta 2 plus beta j Vj equals to 0. We know that Vt equals to V lambda, that is your Vi of t equals to Vi lambda I. Then this can be written as, consider V1 V1 plus V2 V2 plus Vj Vj of all t equals to 0, then V1 t, then this in place ब्रैकेट में लैम्बडा 1 V1, अगर यहाँ पर मल्टीप्लाई कर दोगे और 2 माइनस 3 कर दोगे लैम्बडा 2 minus lambda 1, so which is not equals to 0. So equation 4 is the shortest relation than 1 between V1 V2 and Vk, which is a contradiction. Therefore V1 V2 Vk are linearly independent, which completes our proof. Okay, thanks for watching this.